In this video, I'm going to talk about what is model validation and what are the simple ways of doing model validation. Well, when we build a predictive model, we expect the model to work or to perform well in the new data. So what do we mean by the new data? Well, the data that we use for building models is historical data, or known as the realized data. We already know what is the target value in the historical data, right? In new data, will not have the target variable, right? So we will try to predict the target variable in the new data. So that is the main purpose for building a statistical model or a predictive model. So how do we ensure that the model that we have built in the historical data is going to work fine in future data? Because future data is not yet realized or not yet created, right? Maybe the model that we have built is working fine with the historical data or the sample data that we have taken, but it may not work fine in a completely new data, right? So and why is that so? Because there is certain features of the data which is which is a part of the historical data may not be the same in future. Our assumption here is that there is an assumption in most statistical model that the history is going to repeat, or the pattern in the history is going to be there in the future, but that may not be the case in reality. Okay, so how do we ensure that we at least know that it's going to work, if not accurately, but to a large extent? So what do we essentially do is, when we build model, we have the historical data with us. We create a sample data from it, right? And we create two subsamples from the sample data, right? So from the population data, say for example, if you are building a scorecard model, right? So you will not take the entire population from your portfolio. You will rather take a sample of it, say 100,000 customer data. We divide this sample data into two data sets. The first one we call it as a training data set, and the second one we call it as a testing data set or validation data set, or also known as holdout sample or holdout data set. Okay, all three are essentially the same with different names, different jargons. So why do we do that? Well, we divide this data into two subsamples, and we build model on training data and test the model in the testing data. Now training data, it acts as the historical data for us, and we build the model using training data. And in testing data, we do not use the target variable, rather we try to predict the target variable using the model which we have built using training data set. Now that this testing data is also part of the sample data or the actual historical data, we already have the target variable, right? Now we have the predicted target variable, and the actual target variable, right? So we can compare and see whether the model that we have built using training data set can actually perform well in a new data set. So this is our new data set, right? We assume that this is something of this kind is going to be there in future. So since we do not know the future or what kind of data we'll be receiving in future or we'll be getting in future, at least we can be sure of the fact that any new data set, the model is performing well, right? So the model parameters are compared across training data set and testing data set and ensure that it is consistent. right? So that's is known as model validation, and there are different forms of model validation. Okay, so this is just one form where you create two samples, training, testing, build the model in training data set, test it out in testing and validation data set, check some of the statistics like mean square error, like you want the mean square error to be minimum, and you want it to be minimum especially in testing data set, because that's what matter to us more. Okay, and that's how you validate it. Okay, now there are other kinds of validation as well, so let's go one by one. You can also do validation by taking a number of holdout samples. You do not just restrict yourself to one holdout sample. Instead, you can take a number of subsamples from the historical data. Say for example that you can see, so you have this training data set with you, and then take a number of holdout samples from training data set or the original historical data that you have, right? And the moment the model is ready from training data set, say the model is ready, then you try to predict or try to use this model to predict the target variable in all the holdout samples, right? And see how the model statistics are changing, how the performance of the model is. So what do we mean by the performance of model? Well, the performance of the model can be measured by looking at the mean square error, by looking at the R square value, or if you are you're using a logistic regression, you can take a look at the concordance or AUC value, right? And see whether it is similar to what you are getting in your training data set, and whether it is actually consistent across data set. That means it is irrespective of the sample that you are using, you are actually getting good performance, right? So compare the error rates or whatever performance matrix that you are using across this holdout samples and see whether they are consistent or they are similar. So this is typically known as a resampling technique, where you take a number of subsamples, and this is a popular technique when you do not have sufficient data to have training and testing data, right? You do not have sufficient data, so you take a number of subsamples. Even otherwise you can use this technique, it's not very restricted. You can always use this. And now the next one is out time validation. Now the question here is that maybe the model works in all the subsamples that we have taken, and it works, the performance is good, it works fine, but the model that we have built, say or the data that we have taken for building the model is from year 2005 to 2008, and we are going to use this model in future, right? Say we are building the model in 2012 and we have taken the data from 2005 to 8, okay, or maybe we are in 2010 and we want to use this model for 2 years, from 2010 to 2012. Now we want to have an out time validation for this. So what is that? We'll test this model output in a period which is outside this training data period. The training data period here is 2005 to 2008, and I'm going to take the out time data from 2008 to 2010. Now this data from the year 2008 to 2010 is not part of my training data, right? So training data means the data set used for modeling. So this is completely different data, right? And why do we do that? There are certain characteristics of data that keeps change over time, right? A number of times we deal with time series data where we find out seasonality. We also come across what is known as a structural changes. That means because of policy related like macroeconomic variables. There are some policy related variables which might change, right, in future, or number of data you come across, or attributes you come across which will change, or likely to change in future. So you always expect that the model that you have built in time data actually works fine in the out time. So you take the performance measure of these two time periods and try to see whether they are similar, whether they are close by, or they are very close to each other. If it is fine, then you ensure that the validation is perfect, and you can always implement this model. Otherwise, it has to be there's some tweaking has to be done in the model to ensure that any likely changes in the future, for that the model is ready, or the model is efficient enough to capture that change in future, right? So that has to be ensured, or it has to be taken care of in the model. The next type of validation is across modeling techniques, right? So when we build a model, whether it's a regression model, or whether it's a classification model, or it's a unsupervised learning model like clustering, right? Whatever be the model, you have several way of modeling your data, right? For example, if you are using a classification, you want to classify good customers and bad customer in a credit card portfolio. In a credit card portfolio, you want to classify good and bad customers, right? So you can use a number of statistical, computational, mathematical, econometric, whatever you call it, number of techniques, right? You can use logistic regression, you can use discriminant analysis, you can use decision tree, support vector machine, boosting, any number of techniques are there, right? Now, sometimes it is very clear to us that which technique will be best suited to our data, but in a number of times, even if you are a seasoned modeler, it is difficult to find out which technique really suit our data. So it's difficult to know that which technique suits our data best. So it is always good to build model in using different techniques, and do the comparison across this modeling technique and finalize the model. So validation of the models also happen across different modeling techniques, and the one which best perform is used in future. Now the question is whether the performance should be checked in training data or testing data or holdout data. Well, the performance is always looked at the testing data. If logistic regression performs very well in training data, but discriminant analysis performs better in testing data, one would go for discriminant analysis instead of logistic regression. So that's important. So your performance in the holdout data or training data, testing data is extremely important to look at. The next way of doing a model validation, is looking at the performance of the model using different matrices. So there are a number of performance metrics that you can use to verify that your model is performing well. Of course, it depends on what kind of technique that you are using. So if you are using a classification technique, then you will have a number of classification technique related performance parameters or performance matrices, and if you are using a regression type model, there are different. So sometimes it is actually and there is a difference. Actually, there is a difference between the way you will track your performance using one statistic with compared to the other. Let me give an example. Say for example, you want to verify how the model are doing by in terms of identifying the number of good customers, right, in a credit card portfolio, right? And you're least bothered whether I'm sorry, bad customers, okay? And you're least bothered whether the good customer identification is actually good or not. The model is actually doing very good in terms of identifying the bads, but it's not doing so good in identifying the goods, right? So, and it so happens that what matters to you is identifying the bad. Well, this is a business requirement. Let's assume that. So, even though the concordance statistic is good in one kind of model, if the other kind of model is actually doing better in terms of identifying bad, you will rather go in for that second model which identifies bads in a better way than the first model, right? Because concordance or AUC will take care of both good identification and bad identification. And the business requirement is that you're not bothered about the good identification. You are more bothered, you are more careful about the bad identification. And that's what matter to you, right? So that is more important. Sometimes it's not the performance that actually matters. Sometimes you may need to look at the model estimates, the actual beta values of the regression model more than the actual performance. And why is so? We build model for two regions, right? Firstly, for prediction purpose, and secondly, for inference, right? Now these are jargons. Don't be worried. When we talk about prediction, we try to predict if the customer is good or bad, or we try to forecast something. So that's more about prediction. Inference is about knowing the relationship between attributes, right? Relationship between dependent variable and independent variable, right? So that's what inference, that's what we mean by saying that we want to infer something from the model. When our motivation is inference, or objective of building model is inference, sometimes we may have both prediction as well as inference, but a number of times you will see the major objective will be one of these two, right? So if the major objective is inference, you need to be very careful about the model estimates or the beta values. Now we expect that these beta values are consistent across time and sample, and these are not very sensitive to the changes in the data, because data is likely to change in future, and if your beta values are not robust enough, then it might change, right? So a positive relationship can turn out to be a negative relationship in future. So that needs to be taken care of. So in place of looking at the model performance, if your objective is knowing inference, you should see that the beta values of your model are consistent across all the sample techniques, or all the samples that you have taken for validation. Like if you have taken a number of holdout samples, the beta values should be similar, right? If it is negative in one sample, it should be negative in second sample, third sample, and so on. If it is 0.5 in the first sample, it should be somewhere like 0.5, 0.49, 0.48, 0.51, something like that. Should not be like 0.3 all of a sudden. Then there is something wrong with the model, right? And you can also, of course, use a number of other matrices like mean square error if you're using regression, confusion matrix, and we'll talk about confusion matrix in another video. If you're using classification like logistic regression or discriminant analysis. Validation of models can also be related to the regulations that you are coming under, or the supervisory regulations, a framework that you are following, right? And this is a case mostly in financial risk models, where a number of regulatory points are to be followed while building the model, while finalizing the model or implementing the model. Okay, so there are a number of regulatory bodies, international, like the Basel committee, and there are also state specific regulatory bodies, right? Like in the US Fed, uh, or European Bank, Central Bank, or like Reserve Bank of India. So these are the state specific or internal regulatory bodies come up with a number of regulation related to the model, and the model has to be validated against these regulations. So regulations could be data quality, like if you are not under any regulation, you can use any type of data as long as you are happy with its if it is able to give you good prediction. But regulatory bodies will force you not to use certain kind of data, irrespective of the fact that whether it gives good prediction or not, right? So that's one thing. Then you are not allowed to use a number of attributes, a number of variables in a model because of region cited by this specific country, or the international body. In risk models, a number of times you will be restricted to use the client information, right? You cannot use gender as one of the independent variable in number of financial models, because you cannot discriminate against gender, right? Although it could actually be a very good variable for prediction purpose. So that's one restriction. So a number of this data validation has to be done before you even go in for model validation or model finalization. Then a model has to be validated against a number of assumptions given out by the regulators. Performance, as we have already seen, is also an important factor for the regulators. So they have some benchmarks. So the model has to perform well with respect to the benchmarks, right? So these are certain validation that one need to do for financial risk models and models which are under regulators.